Welcome to Inside Physics. In this session, we will see how does a potentiometer works. What is a potentiometer? See, this is an actual application of Wheatstone bridge. The Wheatstone bridge works on the principle of balancing condition. At the same time, this is also works on the principle of balancing condition. A bridge is nothing but a circuit. We have made a simple circuit. What are the instruments to make this potentiometer? See, here is a battery which will supply the power to the circuit, a rheostat which is a variable resistance. It is a key. It means we can put the key open or closed whenever we want to require the power to be shown into the circuit. So this A to C, if you observe point A to C, we have taken a wire which is bent or which is taken into small parts from here to here, here to here, and these wires. This is the wire, but these are not wire. This is the metal strips which connect this wire. See, potentiometer has a wire which is connected in between the battery and the rheostat, and this potentiometer is actually we apply this to compare two EMFs of two cells. If this one and this one, if you can see, this and this are two cells connected to this potentiometer. So one of the application of the potentiometer is to compare the EMFs of the two cells. And what is the second application? In second application, we will calculate the internal resistance of a given cell. So these two are the applications of potentiometer. So how does it works? See, this is the wire I have already told you, which is taken in this way. So these wires are connected by metal strips. This is the metal strip which is shown in the thick part. This is the metal strip. Why they are connected like this means, see, this has a particular length. When you actually measuring the length, we will measure the length while calculating the balancing condition. Observing the balancing condition, we will calculate the length and apply to the balancing condition to compare the EMFs of two cells. So first of all, this battery will be projecting some current, and the variable resistance rheostat will actually fix some resistance for the circuit. Now see, when we are actually projecting for this battery, the EMF is shown as epsilon 1, and in the first part we actually connect this 1 and 3. So the balancing condition is done for this cell, first cell. So if you consider the potential drop across the wire when you are moving from A to the point like this, when you are moving away from the point A on this wire, the potential at any point of the length, is given by phi L. So L is any length measured from the point A. This is the point A. So epsilon of means you are actually calculating the potential at any point which is considered from point A. This phi is nothing but potential drop per unit length. Potential drop per unit length. When you are moving away from the A on this wire, the potential will be dropping down because of the resistance of the wire. So in this way we will actually consider the two cells. First of all, we will connect this 1, 2, 3, 1, 3. These are the pass keys which will actually connect If you want to connect cell 1, then you need to connect 1 and 3. If you want to connect cell 2, you need to connect 2 and 3. These are the two-way pass keys. This is the two-way, 1 and 2. So this can also be connected, and this 2 is also be connected. First we will connect this first cell to this galvanometer, and this 1 and 3 are connected. Imagine. So here applying the Kirchhoff's loop rule, if you consider when you are connecting this first cell to this 1 and 3, then A N1 G 3 1 epsilon 1. So this becomes a loop. Why that becomes a loop means, when you connect this cell in this circuit and to the galvanometer, when this jockey, this is called a jockey and this is the second jockey, but this is not actually a second jockey. When you are considering measuring the length for the cell 2, this is already shown as the second length. So when you are measuring the length here away from A, at exactly point N1, the galvanometer shows 0 current when the cell 1 is only connected and the jockey is moved on this wire. This is a movable jockey, and exactly at some point anywhere on this wire, say suppose N1, at N1 the galvanometer shows 0 current. That means the balancing condition is achieved. So at this point we apply the Kirchhoff's loop rule to the loop A N1 G 3 1 epsilon 1. For the loop, A N1 Z 3 1 epsilon 1. So what we apply here means the second law, Kirchhoff's second law or loop rule or voltage rule says the sum of all the potential differences across a closed loop is equal to 0. In that connection, we actually consider the potential in this loop that can be written as phi L1 plus the potential across the galvanometer is 0, and the cell which is having the potential of epsilon 1 is equal to 0. This is how we done with Kirchhoff's voltage rule. For the second cell, it is the second cell. When it is connected, that means we connect the pass keys 2 and 3. Then the second cell is in the picture. Now we arrive at the balancing condition in the same way. The jockey, the wire, the jockey is moved from on this wire from A, away from A, anywhere at this wire, say suppose at N2, the balancing condition is achieved and the galvanometer shows 0 deflection. So for the second case, when cell 2 is connected, we can write the condition as epsilon 2, and again the potential across the galvanometer is 0, and this is taken as the second equation. So solving 1 and 2, we can easily arrive at the condition epsilon 1 by epsilon 2. So by this we can compare the cells and their EMFs with the balancing lengths. So in this way, two cells can be compared with their EMFs. If one of the EMF of any cell is known, we can easily calculate the EMF of the other cell. That is the first application. In the second part, we calculate the internal resistance of the battery of the cell. So for that we will make a small change here. We actually need one cell for which the internal resistance is to be measured, and we will put one more extra key and a resistance box. So I will do some small modification in this circuit to calculate the second application, which is calculating the internal resistance of a given cell. So here I will connect the cell here, and I will put one more key through resistance box. So these two are connected to the galvanometer. So this key can be taken as K2, this is K1. So this is the EMF of the cell, and the internal resistance of the cell is represented by small r. Okay, so when the key is open, the battery is not, the cell is not connected in the circuit. So in that case, what actually we do, this means, see, the EMF of the cell can be calculated as phi L1. Okay, the potential drop across the unit length is phi, and when the key is open, we measure the balancing length, that becomes L1. When the key is closed here, okay, that means the current is passed through resistance box through the galvanometer. Again the jockey is moved. When this key is closed means we put the key here, the current will be passed by the cell through resistance box, and again the jockey is moved on this wire. We will get a length where the galvanometer shows null deflection, that is called balancing length. So in this case, when the key is closed, the terminal potential is written as phi L2. The terminal potential across the cell is given by phi L2, and L2 is the balancing length when the key is closed, L1 is the balancing length when the key is open. That means we are actually taking the balancing conditions with cell and without the cell in the circuit. So here we know that the EMF of a cell when a current I is passing through it is actually given by this equation, and from Ohm's law the terminal potential difference is also given by this equation. Okay, epsilon by V, from these two what we can write is L1 by L2. So when epsilon by V, if you take this one and write the equation, epsilon by V is, see, R I into R plus R by capital R, IR. So II will be cancelled, R plus R by R. So this one can be equated to this equation. So I will equate R small r, that means I will write the equation here, L1 by L2. So we need to measure small r here. Okay, so by simplifying this equation, we can write internal resistance small r is equal to capital R into L1 by L2 minus 1. So this is the equation for measuring internal resistance of the given cell. So So L1, L2 are the balancing lines with the cell and without cell. Capital R is the resistance we have taken through rheostat. Okay, so these are the two applications of potentiometer, where in the first one we have compared two EMFs of two cells, and in the second application we have measured the internal resistance of the given cell. So this is about potentiometer and its applications. In the next session we will see one more interesting topic.